In the previous video, we derived the integrated rate law equations for the 0, first and second order cases. In this video, we see how these equations can be practically used in real chemical reactions. This table shows a summary of the rate laws and integrated rate law relationships for 0, first and second order reactions. And we can use the integrated rate laws in one of two ways. We can use rate data derived from real experiments to determine the order of reaction by plotting the relevant data to see if we can obtain a straight line relationship where we would also be able to determine the value of the rate constant. Or if we already have information about the rate constant and the reaction order, we can use the relevant integrated rate law equations to determine a variety of parameters, including the concentration of reactant at a specific time during a reaction, or determine how long a reaction will take for the reactant concentration to be reduced to a specific concentration. We'll have a quick look at both examples now, and we're going to start with determining the order of reaction. So to determine the order of reaction of an experimental rate data using the integrated rate law approach, we will use the decomposition of nitrogen dioxide as an example. Now this table here shows the real data set for how the concentration of NO2 decreases with time at a particular temperature. And we can plot this decrease in reactant concentration with time and see that from the slope of the curve that the reaction rate is relatively quick at the beginning and slows as the reaction proceeds. Now if this reaction happened to be zero order in NO2, we would expect a plot of concentration versus time to be linear. The fact that this plot is not linear says to us that this reaction is not a zero order reaction. So if the reaction was first order with respect to NO2, we would expect a straight line plot when we plotted the natural log of NO2 concentration versus time. So what we're able to do is calculate the natural log of these concentration values and place them in our table. And when we plot the natural log of concentration versus time, again we see that the resultant plot is not linear, and this therefore again indicates that this reaction is not first order with respect to NO2 concentration. Now if the reaction happened to be second order with respect to NO2, then we would expect a straight line plot when we plotted the inverse of NO2 concentration versus time, and that the slope of this straight line plot would be equal to the rate constant K. So we can take the inverse of the NO2 concentration values and add them to our table, and this time when we plot 1 over the NO2 concentration versus time, we see that we do in fact get a straight line, and this indicates that this reaction is second order with respect to NO2. Now we can determine the slope of this curve by calculating rise over run, where we get this equation here, 5.26 minus 2 over 300 minus 0 seconds, to get a slope of 1.09 by 10 to the minus 2 molarity to the minus 1 seconds to the minus 1. And this value, the slope, the value of this slope is actually the value of the second order rate constant for this reaction. So what we can do now is we can actually write a rate law expression for this reaction as the rate equals the rate constant K times the concentration of NO2 raised to the power of 2, since we have determined experimentally that the reaction order of this is second order with respect to NO2. And we've even calculated the actual value of the rate constant at this particular temperature for this reaction by determining the slope of the plot of 1 over NO2 concentration versus time. Now the second way we can use the integrated rate laws is to use them to determine some very specific experimental reaction parameters, and we'll use the decomposition of dimethyl ether as an example here. Now this reaction happens to be a first order reaction, and it has a rate constant of 6.8 by 10 to the minus 4 seconds to the minus 1 at 510 degrees Celsius. You've got to remember that a rate constant is only constant at a particular temperature. You should also note how the units for the rate constants, seconds to the minus 1, match those that we would expect for a first order process. A typical problem we will want to solve may look something like this. If the initial concentration of dimethyl ether was 5 molar, what would its concentration be after 30 minutes? And a different type of question, how long would it take for the concentration to drop from 5 molar down to 3.5 molar? Now, given that it's a first order process, we use the first order integrated rate equation, and we can now substitute in the real reactant terms being dimethyl ether or CH3,2O. To answer part A, we note that the reaction time is 30 minutes, which equates to 800 seconds. The rate constant K is given as part of the question, 6.8 by 10 to the minus 4 seconds to the minus 1. The starting concentration of dimethyl ether is 5 molar, and the final concentration after 1800 seconds is what we're actually trying to calculate. We can substitute those values into the first order rate equation to get this value here, where we see that the log of the concentration of dimethyl ether at 1800 seconds is 0.385, and solving for concentration by calculating e to the power of 0.385, we get 1.47 molar. So in other words, after 30 minutes of reaction, the concentration has fallen from 0.500 molar to 1.47 molar. And this is a very useful calculation to be able to do. Now, to answer part B, how long will it take for the concentration of dimethyl ether to drop to 3.5 molar? We use the same first order rate equations, but in this case, we note that the time of reaction is actually the experimental parameter that we are trying to determine. K is again given as 6.8 by 10 to the minus 4 seconds to the minus 1. The initial concentration is again 5.00 molar, and the final concentration is given as 3.5 molar. Substituting in the relevant values, we get this, which can be rearranged to make T the subject of the equation, and we solve for T and find that the time taken will be 525 seconds or 8.74 minutes, and that's how long it's going to take for the reactant concentration to drop from 5.00 molar down to 3.5 molar. And again, this is a very useful type of calculation to be able to carry out in real world applications.